Okay, I've taken to the relativistic slide rule with Ocker's Raisin because I wasn't getting anywhere with my quantum oscillator, so it's I've stripped it down, simplified it, and haven't lost any mathematics, which is the key, but I've also seemed to have acquired some physical insights, because the big question is if the universe is using the relativistic slide rule, where is it? It's obviously not now our three-dimensional world, 3D world. So let's say that it's in the quantum realm, and let's say that this is the x-axis along here, and that the x-axis has a width, and that width is the Planck length. So from here to here, that's the Planck length. Okay, and the same applies to the y-axis. It's got a width of the Planck length, and the same applies to the z-axis, which would be coming straight out at us. So I can't show that, but it's coming towards us out of the screen or into the screen. So I've got this capital B set to the square root of 0.5 because that's, I think, how light travels inside the quantum realm in an uncollapsed state. And I've got a little b, which is I think represents charge. So it's like the big B represents mass, or the path of a mass, but the little b represents the path of a charge. So at the moment you can see that a photon travelling through the vacuum in the quantum realm on any axis in our 3D world is got a charge of 0. Don't be fooled by that negative 2.22 times 10 to the negative 16, because obviously the square root of 0.5 squared is 0.5, and 2 times 0.5 is 1, so 1 minus 1 is 0. So you can be sure that b is 0 at the moment. And also using the geometry, which is, you can see that there's no b. But let's back it off a bit to say 0.5, and now we've got a b is from there to that red anion, so it's got a value. And what is its value now? It's 0.5. Okay, so anions can have any charge. They can't exist in the three-dimensional world, but they can exist in a two-dimensional world. And unlike matter, protons and electrons, they can have a partial charge, but a non-integer charge. So here anion's got a charge of 0.25, 275, whatever. But they did an experiment, and they found that now I'm just going to create a capital B value, which will give me a partial charge on the anion of a third. So to do that, I'm going to put in little b a third, and that's the formula which gives me my big B. So you look at little b, see it's a third, so the charge is a third. So you look over here, that's 2/3, that's a third. So this blue anyon's got a charge of 1/3, that red one's got a charge of 2/3. So I think that quarks are anyons, and that's why we can't see them in our three-dimensional world, because they can't exist in a 3D world, only in a 2D world. Alright, now what happens when this quantum realm collapses, when a photon collapses, collides with something? Okay, well, in that case, B can possibly go to 0, and in that case you get matter. Here I've got a positively charged particle at the top, and at the bottom I've got a negatively charged particle of matter, and that's because the boson has collapsed. And what happens if we go the other way? In that case, you just get antiparticles at B equals 1. You got no matter, you just got antimatter in this quantum realm. So that's where the antimatter could be hiding, in this quantum realm, with a width of the Planck length. Okay, now you can see my B value is -1. Get that over there. Over here, my B value is 1, so the charge is either 1 or -1. And when you're looking at a photon, the charge is 0. It's 0. And there's nothing outside the quantum realm. So the universe would have started with a one of these, which then just replicates the quantum realm, just replicating, and then when it collapses you start getting matter, and the antimatter just stays in the quantum realm. So you might call that that black circle a complex plane, which doesn't exist in our realm, but we need it to describe how photons move, how light waves move. So that could be I on the x-axis. You could say it's J on the y-axis and K on the z-axis if you're into quaternions or something. See, that's 2, which direct calculated to be the little g factor. But there's an anomalous magnetic moment, so it's slightly over 2. But that's the minimum it can get to.